Hello, welcome. Today we're going to be talking about these two topics. We're going to be talking about estimating the slope of a tangent line and finding the instantaneous velocity, or I should say estimating the instantaneous velocity for some function. Anyway, so first, estimating the slope of a tangent line. We've already talked about this in our last video a little bit about how we can use the slope of a secant line and get our 2 points closer and closer together to try to estimate the slope of a tangent line. So I'm going to go through a problem and show you how that's done. Okay, so this is the example I've chosen. F of x is going to be the function square root of x. We're going to try to estimate the slope of the tangent line at 4. So I've chosen a to be 4. Now here is our definition of the slope of the secant line between the point x equals a and x equals just any number x, f of x minus f of a over x minus a. And as you can see, we can reduce this further down to square root of x minus 2 over x minus 4. Okay, and what we're going to do is we're going to make a table of values, letting x get closer and closer and closer to 4, and then see what the slope of the secant line equation turns into as we get closer and closer to 4. Okay, so here we have the values of x getting closer and closer to 4, starting off at 4.1, 4.01, 4.001. And here we have the value of f of x. That's the square root of x. This is the square root of 4.1, square root of 4.01, square root of 4.001. And here we have calculated the slope using this simplified formula for the slope that we got, square root of x minus 2 over x minus 4. Of course, using a calculator, I calculated all these values. Okay, so what is the slope approaching as x is getting closer and closer to 4? It looks like it's approaching 0.25. Okay, so my guess is the slope of the tangent line is 0.25. However, you have to be a little bit careful when you're taking this approach to estimate the slope of the tangent line, and that's because you're only looking at one side right now as x is approaching 4 from the right side for values greater than 4. What about for values approaching 4 from the other side? Maybe they go to a different slope, and you need to check that. So although this is a strong indicator that your slope of your tangent line is approaching 0.25, you really do need to check the other side. So let's check values that are less than 4 now. All right, there we have it. We now have values that are approaching 4, but from the left side, in other words, values that are less than 4. Here's the value of f of x, or square root of x, for each of those points. And here's the value of the slope between x equals 4 and x equals x. And just like last time, this is approaching 0.25, just like this was approaching 0.25. In fact, they approach different sides of 0.25, but this now gives me a very strong indication that my slope is 0.25. You know, if this was a problem on a homework or a test, you would then say that you would use this table of values to estimate that the slope of the tangent line is 0.25. Okay, so that's estimating the slope of a tangent line, and is just an estimation. We will eventually learn the derivative, and that will allow us to calculate the slope of the tangent line, and without going through a ton of calculator work, which is really what we're doing at the moment, is having to use the calculator over and over and over again, which is tedious, and there is going to be a much better way that comes later. But for now, this is what we have to do. Okay, what about instantaneous velocity? We already talked last time about how average velocity between 2 points in time was similar to slopes of secant lines between 2 points. The slope of a tangent line is the slope at 1 point. Instantaneous velocity is going to be your velocity at 1 point in time. Okay, so it is a direct analogy So instantaneous velocity is basically going to be taking average velocities and looking at your average velocities as your 2 points in time are getting closer and closer to each other, just like we're doing for estimating the slope of a tangent line. We're going to estimate the instantaneous velocity in the exact same way. So let's do an example of that. Okay, so here is the problem that I've chosen to use as an example. I want to estimate the instantaneous velocity at the function h of t equals negative 4.9 t squared plus 10t at t equals 1. So we're going to make a table of values. Let me write down the equation for average velocity between 2 points. So it's going to be our function at 1 point in time minus our function at 1 over t minus 1. Basically the same equation as the slope of the secant line. It's the difference between like f of x minus f of a over x minus a. We're just using t for time instead of x because usually for problems dealing with motion, time is your independent variable. And 1 is the point in time that we're interested in trying to calculate the instantaneous velocity. Okay, so once again, I'm going to make a table of values. I'm going to make my values of time get closer and closer to 1, and I'm going to compute the average velocity and try to estimate the instantaneous velocity by looking at the average velocities. Hopefully they will go towards 1 value. All right, so here are the values for your average velocity. And I have to get pretty darn close to 1 before these started leveling off towards a particular value. Looks like this is approaching 0.2. And so this time I've only approached it from one side. I should probably test the other side to make sure that it's also going to 0.2. So let's do that. I think I'll use a couple less points though. All right, so there we've plugged in values that are getting very close to 1, but for numbers less than 1. And still our average velocity is approaching 0.25. So the instantaneous velocity you would estimate to be, 0.2, not 0.25. So the instantaneous velocity is approaching 0.2, and that would be the answer. And once again, this instantaneous velocity type problem we will be able to solve much later once we learn how to do the derivative, and then you won't have to do all of the calculator work that's necessary for this sort of problem. The reason why this is usually taught in a calculus class is because it gives you sort of an intuitive sense of what the derivative or average velocities and instantaneous velocities, what they're doing. So that's the importance, although I know it is tedious to go through all of the work of using your calculator, especially because at least at calculus courses at UT, calculators aren't used in the exams. So you will not be required to do this sort of thing by hand on an exam. Now they may give you the table of values and then expect you to be able to look at it and go, oh yeah, this is approaching 0.2, that's approaching 0.2, and therefore the average velocity by the best estimate would be 0.2. They wouldn't actually require you to do all of this calculation without a calculator, So I know it's a little bit funny to have problems on your homework that require calculators, but you will not see problems exactly like them on a test. They will modify them in some way so that a calculator is not required. Anyway, that's going to conclude this topic. Hope to see you in the next video. Have a good day.